As humans, we are constantly interacting with things that have mass. But where does mass come from? Well, let's take the first 1% of the mass that we can see. Now, 1% seems like such a small amount that it shouldn't matter. In fact, it only contains the masses of elementary particles, such as leptons, quarks, and bosons. But without this 1%, everything we see around us wouldn't exist. This 1% is created by the Higgs field. So what is the Higgs field? Let's start at the beginning. In the 1960s, physicists creating models of the behaviors of elementary particles using mathematical equations had a big dilemma on their hands. The math wouldn't work when they added in the masses of the particles. The physicists would have had to scrap years of work if Peter Higgs, with the help of other scientists, hadn't suggested, don't mess with the math. What if the environment is giving the particles their masses? Suppose that there's a field that goes on infinitely and evenly through space that creates a drag on a particle as it travels through the field. This field is known as the Higgs field, and the drag force on these particles is what we interpret as mass. The more a particle interacts with the Higgs field, the more mass it has. For instance, let's take the top quark. It reacts the most with the Higgs field and has the greatest mass of any elementary particle. Neutrinos and electrons barely interact with the Higgs field and have very little mass. Now, photons and gluons don't react with the Higgs field at all and therefore have zero mass. As a particle travels through the Higgs field, it has to go between Higgs bosons, the Higgs field's dedicated particles. These are present throughout the Higgs field, sort of like how water molecules are present throughout a pool of water. Now, if the particle passing through the Higgs field and between the Higgs bosons interacts with the Higgs field, the Higgs bosons will start to cling to it. The bigger the interaction with the Higgs field, the more the Higgs bosons will start to cling to the particle, creating a bigger drag and giving the particle more mass. To picture this, let's think of a soccer game. You can think of the player with the ball as the particle going through the Higgs field, and the opposing team as Higgs bosons. As the player with the ball dribbles down the field, players from the opposing team will go and try to steal the ball, clustering around the player with the ball, and as a result, slowing the player down. On the other hand, if a player is just running up the field, none of the opposing players will follow her. This is like a photon or a gluon, which slips through the Higgs field with no interaction and is therefore massless. Thanks to the Higgs field, one of science's greatest dilemmas was solved, and even more can be solved. The Higgs field and recent evidence of the Higgs boson have opened doorways into new branches of physics in the Standard Model. They could even lead us towards answers in supersymmetry, which could fill in gaps in the Standard Model, and dark matter. Who knows what other ideas and discoveries the Higgs field will lead us to?